This is Unit 4H. It deals with the use of radioactivity for power and military purposes. So we'll start with a nuclear reactor. So its purpose is to generate electricity, and it needs heat for that, which generates steam, drives a turbine, and so on. But the heart of it is producing heat. So how does that happen? Well, in essence, it's a chain reaction, a very fast chain reaction. And what goes on is we have a very unstable nucleus, like uranium-235, very large unstable nucleus, and that's contained within fuel rods. Now, these can come in all sorts of forms, but essentially they're very thin. They're so thin, in fact, that by themselves they are safe and cannot sustain a chain reaction. There's just too much space around them. What they need is another fuel rod nearby, and they need the neutrons which start the chain reaction to fly between them. So if we have the control rod that comes down like this blocks, and you can see up here, blocks any transfer of neutrons. They're absorbed, and so that makes the whole thing safe. The essence of it has to be controlled. It has to be fast enough to make enough heat to be usable, but not so fast as to be dangerous. So here we have in a little bit more detail this process happening. Fission is the name for these large nuclei splitting apart, and as they do so you can see that they release more neutrons, between 1 and 3, sometimes 4. We're showing 2 here. Now, as we said, if it's dense enough they will strike, or if it's close enough they will strike further nuclei, and so on, and hence chain reaction. So we can see that happening here repeatedly. Obviously it's massively slowed down, but we can see this series of reactions. So this releases a huge amount of kinetic energy. If we think about it on a very small scale, a nucleus flying around is a form of kinetic energy. So that's transferred into heat, and that heats the water, which makes steam, and so on. Now, a nuclear bomb is essentially the same thing, just much faster. So we have an unstable nucleus, we have fission, but we have no control rods. Essentially, two grapefruit-sized pieces of uranium are blasted together, they're bombarded with neutrons, and we get pretty devastating results. So the first one was July 1945 in America. This was the test run, and then obviously a few months later they dropped it on Hiroshima, and then Nagasaki a few days later. Now this diagram here gives some kind of scale. So a bunker buster is a very, very powerful conventional bomb. Hiroshima was far more powerful than that. The Trinity test was actually more powerful than Hiroshima. Bravo was the first hydrogen bomb, where we get fusion as well. We'll talk about it in a minute. The Soviet Union actually detonated the most powerful bomb ever. It was called the Tsar bomb. It was 2,500 times more powerful than the Trinity test. So this is only a little bit over a decade, and we have this incredible escalation in power. Now, this figure here, megatons, so millions of tons of TNT equivalent. TNT is a powerful conventional explosive. That would give us a cube of side 300 meters. The Eiffel Tower is a little bit over 300 meters, so some attempt I've made here to visualize the kind of destructive power we're talking about, and we've got an image here from a nuclear test. So truly terrifying weapons. Now, fusion is the opposite of fission, and we can see what's going on here. We've got two smaller nuclei coming together, so we've got two kinds of hydrogen here. Hydrogen 2 refers to the fact that it's got a proton and a neutron. Most hydrogen doesn't have a neutron. Either way, they fuse together to make helium, so helium-3 in this case. Most helium has another neutron, but as we know, elements are defined by the number of protons. So just to repeat, it's the opposite. It's the bringing together. It's making bigger nuclei. So it's the opposite process. And it's a very powerful process. It's what powers the sun, and we are trying to harness it here on Earth. Now, we have got it to work in test reactors, this kind of donut shape, torus shape. Here you can see one working. But at the moment they're experimental. Up until very recently they took in more energy than they gave out. So that's obviously pretty useless. But if we can get it to work, and it's a big if, it would provide relatively clean, limitless energy. Another approach here is using lasers. In America they're trying to do this, so using the energy from lasers to concentrate and compress. Now, very unusually, the board, and interestingly, have included a piece of failed science in the syllabus, and that is cold fusion. So these two scientists, Pons and Fleischmann, way back in 1989, stunned the scientific world by claiming they could do the same thing in a very small, relatively cold, sort of room temperature device here. So we've got billions of pounds being spent on these devices, incredible feats of engineering, and they claimed they could do it on a smaller scale. Now, unfortunately, they weren't backed up by the evidence. Everyone else went away and tried it, but couldn't replicate their results. So basically, there was some wishful thinking going on there. They were sincere, but they got a bit carried away with themselves. Now, this makes a very important point about the way science works. They had authority. They were, established scientists. The outcome was certainly desirable for everyone. They clearly had an intuition, and they had a theory. They had a reason as to why it worked. But all of that counts for nothing against evidence in science. And that's a really important point, and I think that's why the board has included it. The Royal Society of London, which was founded in the 1600s, has the motto, take no one's word for it. And this was the sort of foundation stone of science. It doesn't matter who you are, how famous you are, how many people say something, or how long they've been saying it for. It doesn't matter. If the evidence isn't there, then the scientific community will not accept it.